Now this is a more extended example in 3D. It's a kind of hybrid between the garage building and this automatic generated form. And again, by packing these conceptions and rotating them this intensively, you get always, in most cases, interesting results. So that's what I find striking. So now I want to show you how this works. So we will construct the thing automatically in 1,000 versions, and we will have an export as we had it to a CAD system, and modeler like Blender for better renderings. So first is we create the wall. So this interior thing. So it's a skeleton. So the idea is that you design your building like a skeleton, like a fish, in a certain shape, and then it's crystallized around, and then you discretize the outer shape. So you have a random wall and a perfectly organized crystalline outer space. And this communication gives enough tension so that this is proper, in most cases, a proper layout. So we start with a random line. The random line is a small function that I can show you how it works. Oh, no. It's just again with these random numbers, but we put them in line, so it's not an absolute point, but it's a delta of the point. So it simply says the next step, where to go the next step, in which rotation. So the length and the rotation of the next step. So it has no absolute coordinates, but the length and the rotation of the steps. So in this case here, I want to have a random line. Random is here, I'll give you more. Random here is 45 degrees, left and right. And then I want to have 4 steps and the length of 2 units. So, and this is how it looks. 1, 2, 3. So if you put that to half, put that to 12, then it's getting, different. So it's random walks. 6, 120. Forget the numbers. You have to run at 20. Make that longer. So whatever. Yeah, that's our random walk. So, in a lot of cases, then we want to kill if the points are too narrow. So these 2 small steps, I want to delete that. So this is with the next function here. It's a little complicated. Maybe I made it too fast and didn't understand the problem properly. Now I say, give a random line, 12 steps, 45 degrees, plus minus. So, and now I say, just if points are less distant than 0.2 units, collapse them in 1. So let's look what happens. So you get the same figure but less points. So that's a design decision. So another parameter. So, and this is so this simply makes it. So this was a kind of lab. I told you Mathematica is always about a lab. And the conclusion of that is this function here, nothing more. And now I can create a wall, always new walls by this simple line here. So it's nothing, it's just to understand the mechanics and the algebra behind that. So now, if you want to get to a table, you simply say this mechanism here, give that a name, like W, and now I make a table of W's 6 by 6 and put that as a grid. Now we have a nice grid of walls. So very straightforward, very few parameters, parametric design of a wall. So, now, next, we want to give the wall a volume. So we do that by creating limbs. So we have our wall with the function from above. Now in each, I'll show you what the result is. So the idea is we get normals. So each point here gets a normal, which is a line which is splitting the angle, half, of a certain length. So that's the idea. Put that to the inward side. Yeah? And do a similar thing with the head and the tails. So we can discuss how that works, or you can look it up. So the code is completely there, how to do that. I gave you, this is a kind of library to do these kind of things. It's the helper functions here. These are the functions, how to do that. It's not a lot. You can look it up, how it works, to get these sections and so on. Make it, for example, then half. Oops. Yeah. Good. Yeah. So, and now, again, to check that, I call that animal, all the things we had before, put that into brackets, it's a summary, call that animal, and put that to a grid. Then we have a lot of species of the same kind. Simple, huh? Just always these steps. So, now go for the facade. So we had the last points, and now we go and simply you simply take these things. From what we did before, say these should be the points, and then you add this line. You say, instead of having, so the wall is black, default red thin are the lines. These are the lines of the head, lines of the tail, lines of the left and the right side. So these are the 4 principal lines. So then you say they should be red and thin and blue, and a certain point side you say these are the points, because you simply take the last coordinate of all these lines. So you take these lines, join them, take the last, and then you have the points, end points of it. Very simple. And again, all this has nothing to do with geometry. It's like turning whatever your symbols, turning it with like this Rubik's Cube, and then say, okay, make a picture of it. Whatever it is. This abstraction is needed. So, and it's always very few. It's just this. And this is to put it on stage, to render it. So if you want to have another point size, another color, no problem, yeah? Now, if you want to go at a polyline, we have these points. we have crisscross order. Therefore, again, we need the shortest tour on the points. We take the last of it, take the points of it, and now we have a sorted list of points. And instead of, we have the points, blue point size, like before, the points, and we simply say lines, and here we are. Yeah, the same like we had before with our sketch. So now again, like this is again the small edges. The same function we had with our skeleton to collapse points which are too narrow. We use it for the facade as well. Now with the facade, it makes no sense to have these 2 points. We want to have one of it. The same here as well. This should collapse to 1 point. So therefore we say our facade should be of the length of unit 1 minimum, and we want to collapse it. So therefore we simply say points should be collapsed in points, nothing. So this is a line, and then we change here from point to point S, that's it. Now we simply say this is closed line. So then we get a closed line. So now this is better. Yeah, getting interesting. So next step is a little tricky. This is a discretization again. So what we want to have is to give that a more rigid body, that the elements of the facade, like with Carrot's building, should be of the same size or multiple of the same size. So in our case, it should be the multiplicity of 1 in length. So it should be 1, 2, 3, but not 1.65 or something. So I have to move the points in minimal distance of their origin, so that all the all the segments of the facade should be of same size. So it's again a communication of topology and geometry. So these things communicate and they struggle, and it's dense. And you're loading this form by that. So this is the function. That's a recursive function. It's a little tricky to do that, but this is the result. Yeah, you have minimal change of the points towards its origin, and always a multiplicity in length of a modular. And here you see the lengths of the facade elements. It's 2 units, 1, 2, 2, 1. Okay. These are all the functions to create this. So this is your model, the coded architectural model for the facade. So this is all needed to create a facade. So you have a wall. Now you have the function for to create the wall. Now you have the function for to create the facade. So these 2 things with the parameters here. Very few code, 2 poems, and put that on stage. So that's it. And here we have a figure, which is not bad. Do it again, and you have another one, which is not bad as well. So, and if you want to have hundreds of it, simply say what is needed. So this is your architectural modeling, your model, how to produce it, how to turn the things. This is putting them on stage. Do that in a grid. That's here. So say this is our building 2 in 2D. Put it here, table 3x6, display it as a grid. And here we are. And all this is not bad. You understand these principles, huh? So this, I think, it's this architectural modeling as code, and you don't struggle with a certain geometry. So you always have certain characters. So in all these elements, they are of the same kind, and they are globally connected because they are all the same. They know these things, and then you can adapt this thing in its characteristic to a certain location. So this is a strong articulation of a form. Each of them somehow works. And your architectural model is abstraction. There's a kind of quantum modeling. So it's an abstraction of drawing these things. So it's coming out of nothing, and it's alienating the environment. And it's still there. Good. Do the same in 3D, or go next step to make it 3D. So we have this wall, we have a height of 1. This simply says what is wall. We can check it like this, and it needs, so these are the coordinates of our wall as we had it from carrots. So, and then we simply say take this wall and have the first, do it for all, this means do it for all the elements of the wall, and they are these points. Then take the element and add a 0. Take the element, add the height, and do it for all the elements. Which means if we do that, and we go for PTS 3D, then you see what happens, 0000001. And then this here with a 0 and with a 1, with a 0 and a 1. And then this here is 0 and 1. So we go to 3D. Very simple thing. So you do it with this fancy line. Yeah? Good. So for the polygon, we need, okay. These are the, okay. This is too much. We need to save time. So, which means if we go now for graphics 3D, go for the wall, it's a function for that, then this is our thing in 3D. Again, the stage, the characteristics of the stage, and these are our actors. So, put that into a function, create the wall in 3D, and now we simply, if we have this library, we simply can do it and have the polygons, put it to graphics on stage, and that's it. So we don't have to care about the specific wall. We simply make them 3D, extrude and polygon. So now with the floor and the ceiling, it's very similar. So the facade is again some points, two-dimensional. So, and we do the same thing, append here, but we don't get these polygons around. We say we want to have one and the other for the top thing. So we have the floor and the ceiling and the wall, and put that on stage, and that's our thing. Again, as as a comprehensive function, create this, put all this together. It's not more than this. Create the facade, and you have these two polygons, and to be displayed like this. Now the facade. The facade is different. So we have parameters. So this is the dialogue of the whole setup. So you have the parameters, parametric wall, and you have the parametric ceiling. So they are whatever the coordinates are, and you have to make them in concrete, and so they are no grid. They're not discretized. So, but you have discretized elements for the facade, and they should be all the same. Therefore, we need a library for that. So this is a design object. So this is, therefore, here we have a graphics complex, the coordinates 000, 10, 0011, and so on. This is, and make that a polygon from point 1 to 2 to 3 to 4 to 1. And that's our facade element. Put that on stage, and that's it. That's our facade element. These are groups in Blender, and then you can make instances of it. And we call it facade element. So now we have to put it along the building. So, floor 3D. It's a polygon with these coordinates. So what we want to have is, in the first step, the sections of the polygon. So the first line, first section, the second section, the third section, and so on, whatever they are. So this is done with partition. Partition of floor 3D. We want to have it in parts of 2, because it's a line from here to here, then from here to here, from here to here, from here to here, from here to here. So this is, we want to have chunks of 2 and an overlap of 1. So, and we need floors from 1. So just the numbers, not the polygon. So, and here you see what we have. That's here the first two elements. And then we have the second and the third element, the third as a fourth element, and so on. So this is done with the section here. So this is the first section, and we call the first point S1, S2, just to set up the laboratory. So, if you want to fix any part, whatever it is, and bring that into a geometry, you have two movements, and we had that always in Blender. It was the same. You have a translation and you have a rotation. You have no mirror, no scale, no nothing. With scaling, we are in parameters, not in planners. So, therefore, we need a translation and a rotation. So we go 3 steps. We go here. So we go here, and then we have to put ourselves in front of it, so then we can fix the thing at this point. And then we go to this point and put a certain thing there. So it's very simple to get these things. So, for example, this is we have S2. So we have this line, this segment. And we want to position a facade element at this point and turn it to this point. So, and move it so that it fits the line. So, the first point has this coordinate, S1. The second point has S2. So, we can say rotation, transform, off. And then we can say we want to have 100, 2, S2 minus S1. So then we always have a reference system around the origin of our coordinate system. We just want to have the rotation, not a transformation, because we don't want to rotate it like this. We want to rotate it around its origin. So therefore, we say it's origin, and the vector of reference is just x direction. And then we look, what is our segment? Second point minus the first point, somewhere here. We take this and move it here and have the second parameter. So we have the first and the second. And then we want to get the angle. That's our rotation. So this is straightforward and done with this function here, and we get a transformation matrix. So you can look it up, look what it is good for. So this simply says how to translate, rotate, and scale in one machine mechanism. So, and these numbers represent a certain rotation. So, the same, so that's here. The same with the translation, which is simply very simple. You have the origin is where it is produced, and then you want to position it here, so you simply take this distance from here to here, and that's it. So it's simply S1. So, and the beauty, now I can show you this, it's again a transformation function. This is about rotation, and this is about translation. And the overall thing is with scaling and so on, you can have it, look it up. So if we combine that, we need this dot product. So translation and rotation, so this is the actual assembly. Both combined is dot product of these two. And we get these things combined. You see, it's this part and somehow calculated. So that's the assembly. You don't need more. And it's called TF in our case. So we simply say, this is a function how to assemble whatever it is at a certain point in space. Don't need more. So, and now to look it up. So let's so we have a facade element, it's here. So if we put that, so this now is our origin, that's 0, 0, and this is our facade element. So we have everything like normal, so the walls, the floor and the ceiling in a certain opacity, grayness and so on. And our facade element at its origin is in x direction and at 0, 0, which is always this starting point of the wall. So if I now put it like this, that I say graphic transformation of this element with this transformation function, then it goes to our edge. That's it. Yeah? Always these stories. Now it's about the lambda calculus. Put it to a comprehensive function. We have it here. Now we have to speed a little up. Now it's just the lambda calculus. We do it with all the elements. We can discuss that. You need this helper function. Put that to the code. Then you have all the transformation for all the elements. Very simple. So, and here you have the facade in 3D. Put that, and then you have it. So it's very 2 lines to make it with the whole world. So that's the beauty with the calculus. You can do, it's always the same. Do whatever you like and puff, you have everything. If you get the principle. So again, a comprehensive function. I call it assemble the facade in 3D, and this is our 3D facade. Now the whole building, the wall, the facade in 2D, wall, floor, ceiling, facade in 3D is here with this predefined function, part of our design. Putting that into and onto stage, we get a building. And put it again, we get another one. Yeah? So, put that as a simple function. Now this is the simple function for a 2D version. This is a simple function for the 3D version of that. So we have 2D, 3D, buff, done. Now get the 2D buildings. That's a grid, table grid, 2D. Now we have nice buildings here. Export them, for example, to PDF. Just take this building, one of these buildings, create a new one, put it at A01 PDF in this folder, A01 PDF, and here we are with a new building in PDF. Make another one. There's another one. It's always somehow working. So now with 3D, again, put this to a symbol, make the grid out of it, and now a grid of 3D buildings. Same logic, just other symbols. And here we are with 3D buildings. Export that as a PDF. It's A02. And have a nice PDF. Or you can export it simply by saying 3ds, and then you get a 3D model for a CAD system for that. So if we go, then now we have 3ds. Go for, you see what the problem is. Import 3ds. So here we are with the geometry. The facade is not there. So what you can do easily with all these formats is get separate elements as graphical things. So it's one mesh. If you look it up, it's a single thing. You see, it's one mesh. There's no, in this case, there's no, it's just one plain thing. So you can play around a little with different export formats, with different options and so on. So what I did now is, and the elements of the facade are not there. So they don't get the structure of your architecture. So therefore, I want to simply show how this works. This is the interface we had for Mathematica to Blender. So this is one of our design. Here. Now I wrote a code for getting the polygons to Blender, reading these specific polygons of the wall. It's here, and this is a Python code for that, so you need this code to do it. Do the same, I did the same thing, so it's working for ceiling and floor as well, specific code, so this there, and you can do it for the elements. Now I have a complex Blender, so I make this library element here with that, and I have the instances here. So now I can, which means in the in the way we discussed or I presented in a pre-lecture. So I directly can go to this. It's a copy now the structure of my architecture to the potentials of a CAD system. So the problem is that if you code, it's always like Rubik's cube, and the CAD system is always layered and structured and so on. It's very rigid. So therefore, you have to say how to put it and how to organize it, so to keep a certain structure and so on. So in this case, I say I want to have a block. It's called prototypes. So this is the hierarchies in the outliner. This is here. This is here. This hierarchy. So and I say this is from scene, which is the top node. I want to have a sub node called prototype. Then one with a side. So then I want to have two materials, glass and concrete, and take it from a library. So then I create this from the graphic complex. So this is our graphics we had for the facade element. Put that to Blender. And then I got the polygons from the wall, the ceiling, and the floor to Blender and give them these names. Facade element W1, C1, F1. So then I say I want to have a group because this is a design object, my facade element. So they have to go for a factory for that. That's a group. I add this facade element to this group. I create the facade element and I add it to this group. Then I create the object for the ceiling, the floor, and the wall. It's here. Put it on layer 1. And then I made all the instances for the facade element. All the facade elements, put that instance to Blender for these facade elements. So this is what I wrote. Export that as text1 to this directory. So that's the code. If we want to look at it, I can show you the code. So this is a Blender code, nothing more. And in Blender we can look it up, get a new one, go for the text editor, go here and there, test one. This is our code which is creating all the structures and all the elements with materials, loading it from library and so on, as discussed previously. Cancel. Wrong. Now go to no. We have to run that. We see now we have prototypes site. We know we have objects with different names of facade elements. Go to 3D view. This is our library, and this is our object. And if we go to material or to rendering, no. So now we can work with it. So there's no lighting, no nothing. So, but you have a structured way of your building directly there, and ready to have that for hundreds and thousands of that in versions. So that's the way. This is what I wanted to show today. So with the exam, it's very simple. What I think, what we do, I prepared. You see there are about 60 of these tutorials, crisscross around. There's a set of tutorials which are very basic, so in a very few minutes you can check these things. And you should learn them. There are this set of 7, they are for mid complexity. And I think I want to examine this. So the exam will be that we invite you at the end of August. It's defined, I think, the 28th in the morning, 3 hours. We invite you and you get a mail for that for half an hour in groups of 30. So then you by random get one of these tutorial. So with a picture that you know, and then we want to see that you're able to do that within half an hour, without major help. So therefore we see you at your computer, we are walking around with 5, that you're not cheating and copying or whatever, so you really are able to do that. So, and we want to get you trained in this tool, and the exam will be like that. Relatively simple and straightforward, and so there's a lot around in the tutorials which goes beyond these things. Hope you find that this interesting you to continue with that. The same thing with the lectures. It's a lot of stories around. I find that very, very important to do that. But I think it's super complicated what I'm always telling to exam that. I don't know really how to do that. And therefore now with these kind of simple doing in these things, it's a good step for this exam. So we will not have questions this semester, and I have to improve that. This didn't work last semester with the questions, so you all easily had no major mistakes and too few. So this was. I don't want to have you learning these things by heart. I want to get you involved in thinking about what computing is about in architecture and how this can improve your modeling and your skills as architects and so on. So, and obviously with these question, a random question, does not work. So, because you simply learn it by heart, so which I didn't expect in this to this degree. So I have to get creative there for the next semester and make the next try how to make that. So this exam will be relatively simple and straightforward with this one out of these 7 exercises. So you will get a mail, and that's it. Next semester I want to focus on big data, the internet, and how to deal with the plenty. So we will be able to look around in the internet and load thousands of, 10,000s of pictures, videos, texts, and so on, and being able to analyze that. So you will have a library of all the architectural theories, and then you can start writing some text, and then the whole library responding to what you are writing there. You get all the references, so these are all your colleagues, dead and alive and so on. They wrote books, and then you can write a certain thing, a certain hypothesis about architecture, and then they answer. So you get all the answers, what they're saying to that. So I will show you how this works, and you will have an instrument that you're able to do it like that. Similar things with pictures, similar things with movies, and so on. So, and then we will talk about privacy, we will talk about encryption, the blockchain, all these principal technologies needed in the internet. I will show you how to write parsers that to get all these tons of data. So we will discuss these things which are prominent these days, and I think which are very important for your career and for your understanding of what an architect is. And therefore I think it's very important what you've seen today. We have these crawlers, for example, running for 1.5 years now, and they are crawling 50,000, so very small computer, Raspberry, and this is crawling 50,000 floor plans a day. New things. Then we go so you have to deal with these plenty somehow. Therefore, I think these kind of exercises and the thinking is very essential, what I showed you. That it's not the single thing which is important. It's always a lot, a plenty, and you have to organize, and you have to keep that under control. And this is what I think is the richness of a building, that it knows all this, whatever it means. Yeah? So next semester we will be on the plenty and work on that. So thank you, and have a good time. See you.